So today we get that component that's going to make derivatives much easier in my humble opinion. Okay, and I'll show you some examples of what I'm talking about, but the one thing we haven't been able to do is take the derivative of composite functions. Matthew, what's a composite function?
It's a function inside a function.
Good. Can I have a function inside a function inside a function?
Yeah.
Would that still be a composite function?
Yeah.
Beautiful. Okay, so, be nice if my clicker worked. Let's do a little review here. Go ahead, take the derivative. Whichever method you'd like, because we've talked about two different methods. What are you doing? Multiplying out or product rule?
Product rule.
Good. Next group.
Multiply
it out. Multiply it out.
Product rule.
Oh, look, same.
Sorry, I just see it.
It's adorable. You won that half of the board.
Oh, I'm scared. Okay. Yeah.
Wait, I don't know if we can do two. Go ahead, try it. Start writing then. I'll try writing. I don't know if it. It doesn't work. Okay. When she's done, you get to do the five. Don't look at me in that tone of voice.
I did the other one though. We did
Well,
the product.
oh, they did. Sorry, you're going to multiply it out.
Oh, got it. Okay.
And hopefully your answers match.
I did, yeah. I just see 14 times 3 is. I do the y. 3 times 3. I don't know why it looks like a triangle. Oh, I got 12 eyes. 14 times 3 is 42. No, yeah. Thank you, Emily. I got negative 32 x squared.
Faith, don't bother simplifying too much.
Oh.
Get the basics in there. So go ahead, finish what you're doing.
Okay.
But you don't have to take it all the way to the end.
Okay.
And
I'll
once
just.
you did, and you can just put a final answer so we can check. Whatever, just go. When you're done, pass it on.
Okay. Oh, well, either way, if I can combine these together.
Okay, so what degree is that equation? Good. So what do we learn about taking the derivative? If you take the derivative of the fourth degree equation, what should your answer be? Okay, so that in itself is a check that you might be right. But then again, you couldn't believe it's for yourself. Okay, for those of you that use product rule, you can see that Faith put the product rule up there. Hopefully you have the same answer.
Yeah.
She took it all the way to simplifying. While Delaney's doing that, I'm going to talk a little bit about what we talked about the other day. Mr. Zimmer, what degree is that expression? It's a 4. So what happens when we take the derivative of a fourth degree equation? What happens to the degree? Goes down 1. So that in itself tells you that Faith might be on the right track because she has a cubic as an answer. Where are my multiplied out people? Raise your hand, please. Okay. Check her math when she's done before she starts taking a derivative.
This is very scary.
That's okay.
Okay.
It'll even get weirder when you get really close to the edge.
Oh,
See,
God.
that happens. That's okay. Just click somewhere else. You'll be fine. Good.
That's 35x and 28, but you can't really see it.
Yeah, we agree? Okay, so they're all agreeing with you, so go ahead and take the...
Sorry, guys. I'll
Take
start
the
over a little more.
derivative. You have a question? You just wave your hand.
This is a 4. That's a 4.
Good, good.
Don't I have to put like...
Just leave it. We're going to talk about that in a second. I'll take that from you. Thank you. Okay, so let's talk about notation a little bit. What does this mean?
Derivative of that function with respect to x.
Good, the derivative of that function with respect to x. So when you take the derivative, this puppy will disappear. Okay, because you've already taken the derivative. We'll just do that. Okay. Just clean it up a little bit. You know, probably what I should have done is called this f of x, and then we'd have f prime of x. Okay, good. Two methods. Entirely up to you what you want to do. As the functions get nastier, you probably are going to start to shy away from multiplying it out because your polynomial gets horrendous. However, if you spend the time multiplying it out, your derivative is pretty simple because it's just an application of the power rule. Okay. Problems, questions, concerns? You'll notice I didn't do a quotient rule because we're going to talk a lot about the quotient rule today, okay, using the chain rule. So today we're going to talk about, as we already discussed, how to take the derivative of a composite function, what happens when you have a function inside a function. We're going to simplify some stuff, and this is, remember when I talked about, oh, just leave it in that form, we'll worry about that later? Yeah, today we start worrying about that. How are we going to simplify these nasty derivatives? Do we leave it with negative exponents? Do we have to get rid of the negative exponents? Do we look for a common denominator? Et cetera, et cetera. We're talking about some trig functions, because life wouldn't be complete without trig functions. And in fact, we'll talk about trig functions with functions inside of trig functions. And you should be able to recite the state capitals. Anybody? Josie, you think so? No? If I had a map that's cheating, the state capitals would be on the map. Wait, hold on. So you're saying you can recite the state capitals, you just can't remember the states.
No, I know the states.
Yeah.
Oh, that's me. See what they look like, to see which one has which capital.
So if I had one of those kids' puzzle pieces, if I just threw a state at you, you could go, oh, that's Ohio, it's
Columbus?
Columbus. I knew that, I was just testing you. Good job. Or if I throw you like that little weird Rhode Island, you can tell me.
Providence.
Yeah, Providence.
Providence.
Okay, so maybe you could.
I
You just can't fire off the 50. Yeah.
I only know 3. You're somewhere in there. I only know 3. That's,
Now, before we start this, hold on, before you dive into anything, let's look at something like this. Suppose I gave you this. We'll call this g of x. Suppose g of x was x plus 3 over x squared. Luke, how would you take the derivative of that? How would you find g prime? You don't have to do it, just tell me how you would.
I would do x plus 3 times x to the negative 2.
Beautiful. So you would rewrite this as x plus 3 times x to the negative 2. Who would do it differently? You would all follow Luke like little loyal puppies.
Yeah.
Well, that's what Luke does. I'm going to do the same thing. No one would do quotient rule? Okay, that's why I asked. Quotient rule is another option. Right? Did you say wait?
I said it's easier.
Quotient rule is easier? Yeah. Well, we can fight about that all day long. Personally, I avoid quotient rule whenever possible. I like product rule, but if you like the quotient rule, do the quotient rule. It doesn't matter. And we talked about having the option there that if you don't like the quotient rule, then turn it into the product rule. But what about this f of x function? So we could do a quotient rule, or I could turn it into a turn it into a product rule. As a product rule, that would be 1 times 2x minus 7 to the negative first. Now we have a problem. What, pray tell, is the problem? Cricket, cricket. Maybe I'm mistaken. Maybe there is no problem.
The problem is I don't know what to do.
Oh, that's a big problem. Why don't you know what to do?
Because how do you get rid of that -1 up there?
How would you normally get rid of something raised to the -1?
Don't you distribute it in?
Put it back into the denominator.
No. We're doing bad math. Remember, we're taking a derivative here.
Oh.
Just,
I'm bringing it to the denominator.
but then we'd end up back where we started.
Oh, okay. Don't you drop it to the, oh,
Okay, so this presents a new idea. Go ahead, Kate.
Can you not bring it in front as a coefficient since it's?
Oh, great. So can't we just apply the power rule? By the way, are we all good with just getting, okay?
Yeah.
We're all good with that, right? Oh. So Katie, you're saying I could take f prime of x and just apply the power rule, right?
Well, yeah, but then, I don't know if it would go in front of this at 2, or,
Oh.
I don't know.
I'll give you a couple options. Maybe? Okay. Or we could do this.
No, that's just the same thing as distributing, right?
Is it? Okay, hold on. Let's check this. I'm seeing a problem here. Okay, so there's example, right? No? You sure?
You have to do what's inside.
I swear it first.
Pep does.
Aunt Sally.
Oh, yeah.
Yeah. Okay, this is bad math. Don't do this anymore. Okay, just like we can't do it here either. That's also bad math. So let's get rid of all of that. It's good exercise. Okay. This is also bad math. Now that would work great if the thing inside the parentheses was just a variable like we did with the x squared. But now all of a sudden we're looking at a composite function. Do you all see that this puppy up on top is a composite function? This is important, yes or no? Yes. Okay, good. So if the answer is yes, what are the two functions?
2x minus 7 and x to the negative first.
And something to the negative first. Good. Okay, so that's something you're going to have to be able to do to survive with the chain rule. In other words, identify how many functions you have going on and identify what function is inside the other function. So do you all see the fact that 2x minus 7 is that internal function? And then that function is raised to an exponent of -1. Okay? We're good with that? Here's another example. Also a composite function. Which function is on the inside? X squared. Which function is on the outside? Sine. Good. If you can do that simple task, chain rule will be easy. If you struggle with that, chain rule could be a little more challenging, but through practice you'll get a mastery of it, if you will. Okay? So, we're actually not going to solve this problem yet. We're just going to move on because I wanted to use it as an illustration. At this stage, you'd probably just do a quotient rule and move on. Okay? So, in order to be able to take the derivative of a composite function, we're going to use something called the chain rule. Okay? And as it says, it deals with functions within functions, but we knew that already because Matthew told us that, and we believe him. He's honest. Please tell me you heard that.
Yeah.
Oh my goodness. That's not fun. All right, so on the left-hand column, I have a bunch of functions that you know how to take the derivative of because there's only one function. On the right-hand side, all of a sudden they become composite functions because we have a function within a function. In the first one, this guy, how many functions? 2. What are they, Em? Which one's on the inside?
X squared plus 1,
Good. Which one's on the outside?
the square root.
Or if you're feeling
And
saucy, you
1/2
could write it as to the 1/2 power. Very good. Okay. We can skip the second one because we talked about that already. Adrian, how many functions? Here.
That's it. Gonna be 2.
2. What are they? Which one's on the inside?
3x plus 2.
And the outside?
The fifth power.
Good. And then this one's a little weird. That's just a plain old x. We don't need to talk about that. That guy we talked already about with the sign. Okay? Good. So here's the chain rule. I'll explain the onion in a second. Layers. Right. You have to do it with a Scottish accent. Let's try. Layers, like an onion. Okay, so what we're concerned about is this bottom guy. If we have a function within a function, f of g of x, you take the derivative of the outside function, and you chain on the derivative of the inside function. Then you stop. Okay. There's an onion there because we're going to operate in layers. We're going to work from the outside of the onion inside. Layers of an onion. And that gives you all the fancy schmancy calculus speak stuff that we care about. We want to see how this works in a practical application. So I've got a bunch of examples for you. There is some subtlety, though, in that calculus speak that I want to point out, and that is the idea that both of the functions have to be differentiable. What does the word differentiable mean? Able to be differentiated, yes, which means?
You can take the derivative.
Good, yeah, they're functions you can take the derivative of. If you can't take the derivative of a function, you can't do the chain rule. That seldomly, if ever, happens. But we just want to keep everything above board. Okay, good? All right, let's do this. So, like I said, we want to figure out how many functions we have. Early on, most of the time, we're going to have 2 functions. And when you have 2 functions, you chain once. But as we get more functions in the composite, you always chain 1 fewer times than the number of functions that you have. Okay, and again, that's probably not making much sense, but when you see it in action, you'll understand a little bit better. Okay, so like I said, if you have 3 functions, you chain twice. You have 9 functions, you chain 8 times. That probably won't happen too often. It might a couple times, though. Okay, so here we go. Who's going to start? Dexter, how many functions?
2 functions.
Beautiful. What are they?
2x minus 3 and then raised to the negative 7.
Good. Which one's the outer layer of the onion?
The negative 2.
Good. So if I gave you a function raised to the negative 2 power, could you take the derivative of it? Yes, you could. How do you take the derivative of something? Let's make it a little box thing. What's the derivative of box raised to the negative 2 power?
It's like, I can't tell you. Wait, no, it's the square root. No.
Take a deep breath. Focus. Okay. How do you take the derivative of anything raised to the... Okay, let's try this. What's the derivative of something raised to the 2nd power?
Oh, yeah, you just multiply it. Yeah.
Yeah.
By negative 2.
Okay, so what would the derivative of this be?
It would be negative 2 box to the negative 3.
See, I knew you could do it.
Yeah, I just forgot it.
I understand. You're under pressure. There's a stranger in the room. Right? I understand. If she wasn't here, you would have rocked that. Okay, so we'll blame her. We're going to pretend that we don't know what that thing is. We're going to treat that like the box. So as he said, you bring the exponent down, you reduce the exponent by 1. Okay. I haven't touched that inner function yet because we're still working with the outer layer of the onion. And because he told us there's two functions, how many chains? One. Okay? Dexter?
Yeah.
What's the derivative of 2x minus 3?
It's 2.
Well done. Okay. And again, baby steps. If you can do that, I'm happy. If you're feeling all fancies in your pantsies, you could multiply 2 times negative 2 and get a negative 4 out in front. That'd be impressive. But you don't have to at this stage. All right, so let me stop. This is about as basic as it gets. Questions? Going once, going twice. Sold. Let's move on. Oh, look, there's the work. I got it right. Woo! Okay. Now you're saying to yourself, why do we have to do chain rule? You just said before I could turn a quotient rule into a product rule, or I could use product rule, or I could multiply it out. Do you want to multiply that out? No. By the way, just for giggles, what would the degree of the equation be if you multiplied that out? It'd be a 16th degree equation, and when you take the derivative of a 16th degree equation, you get 15. Good. We're not going to multiply this out. We're just going to go average. Okay? Molly, your turn. I already told you there's two functions. How many chains?
Oh, one.
Good. Okay, so are we taking the derivative of the fourth power first, or are we taking the derivative of the quartic?
The fourth.
You all know what a quartic is, right?
Yeah.
Fancy term for a term?
The fourth power.
All right, give it to me.
4.
Oh, hold on. H prime of x. Keeping my notation clean. Okay.
4.
Uh-huh.
Times everything inside.
Uh-huh.
To the third.
Okay. What's the one chain?
Times. I don't know. 4? Oh, okay.
Yeah. Take the derivative of the inside layer of the onion.
4x to the third plus 6x plus 2.
Okay, we good? No, we're not. What's wrong with that? Parentheses. Atlas says with some spite. You seem very angry that I missed my parentheses. I did it purposely, you know. Okay, good. Rolling right along. This is fun, right?
Yes.
All right, you do this one.
I still have this marker thing. Sorry, I don't know what to do with it. Okay. Now I know.
Thank you for not taking it home.
It was hard to resist.
I know, it's like a little memento of our time together, right?
Yeah. I don't know if I leave out.
If you wanted to. But again, we're not that concerned about simplifying right now. We'll talk about that. You could multiply the 4 by that. Right, let's just bring it into there. Okay, yeah. Okay, good. Problems?
I like this rule. Me
Excellent, yes? Good. Yeah, and that one's not much different than h of x, so I'm assuming you got it correct, right?
Yeah.
All right. I just had a question. And the question was, well, hold on, let me get caught up here. 4 times 5, 6, 7, 8, 9, power, 12. Okay. So I got that. the question is, how can we simplify that? About the only thing you can do shy of multiplying that monster out would be to multiply the 4 times the 12. What you cannot do, again, repeating myself from earlier, is bring that 4 inside the cubic term. Because there's a cubic in front of it. So don't do that. And again, at this stage, I don't care if you can simplify it, because we'll do that later. But until then, or I should say when we do that, these two can multiply together, but don't bring it into the cube. Okay? Would you like me to lie to you or tell you the truth? Tell the truth, you're not going to like this. Some of you have already run into this. Some of you have already run into this problem because you start doing your homework, you do everything perfectly well, and then you look at the pesky answer sheet and your answer doesn't match the answer sheet. And then you think you got it wrong. And then you start to cry, and it's uncomfortable for everybody. Okay? So, the reason your answer doesn't match the answer sheet is because the answer sheet is done by some college grad student who's showing you how smart they are mathematically and taking it to the extreme level of simplifying it. So what we need to talk about is, where do you stop? Because some of these you can just keep going and going and going. Okay? So if we take something like this, we have 2 functions, 1 chain. This becomes particularly nasty because notice that my one function is a quotient rule. So I have a quotient rule wrapped up in a chain rule. I cannot tell you how much fun this is going to be. Okay? It's going to be great. Conrad,
Yeah.
what function is on the outside?
The exponent.
Good. So then you would deal with that first, right?
Yeah.
Now, through the wonders of modern technology, I deal with it by clicking. Whoa! And it magically appears. So, I know some of you are writing like mad people, but try to process what I have in that step. What did I do? Conrad, what did I do?
First you move the 2 in front.
So far, so good.
Yeah, and then you copy down what you have,
Uh-huh.
and then you multiply it by the derivative of the inside.
Beautiful.
And for that, you use the quotient rules. That's why it's like big. Yeah.
Lovely. Okay. So, up until today, we'd say, great, stop, looks great. Never mess with the denominator, leave it alone.
I still say it.
Some of you are too smart because you see where this is going. Yeah. Conrad, what do they do?
You multiply some of the things.
Could you be more specific, please? There's a lot of things up
You
there.
distributed the 5 in.
Good.
And then also distributed in the 3x squared.
Uh-huh.
That's about it.
Okay, what do you think I'm going to do next?
Probably gonna simplify the numerator by distributing the negative sign, and then.
I'm just going to click.
Yeah.
That's all I just did that. Okay, what do they do? Conrad, back to you.
Then you multiplied it by the fraction, or not the fraction, the little thing in the parentheses outside.
Good. What do you think I would do next?
Cry.
No, not yet. We'll save that for a second. I want to try an upper round step too. Any ideas? What would I do next?
Multiply it out.
Yeah, multiply out the numerator.
Yeah.
Right. But notice it says final answer. Why would I stop there? The reason I would stop there is because now I have one consistent denominator and one consistent numerator. Knowing where we're going to go and what we're going to be doing, that is pretty much our goal. Can I get one denominator and one numerator? Then we're going to do some other stuff with that numerator. But until we get to that point, that's about where we want to stop. Now, I want to go back to the very beginning of the problem. As I mentioned earlier, I don't like quotient rule. So I could rewrite this problem as the following. Yeah. So what's going on there? I've got a chain rule again with a product rule with another chain rule inside of it. Because when I take the derivative of x cubed minus 3 to the negative power, I'd have to do another chain rule. You probably wouldn't do that, but I want to show you the possibilities and the dark path you could turn down. That would be where you would start crying. That's about a point where you just grab the box. Go and get some like a half a tube of Pringles and just go crazy on the Pringles. As you cry, you get the Pringles all soppy. Okay, trig functions. We know the derivatives of all 6 trig functions already. But we can build some chain rules with those trig functions. Now, I know you're freaking out, but the only thing that's different on this page than the other page that we had on trig functions is I changed x's to u's, and I stuck a u prime on the end. Well, what does that mean? It's simply the chain rule. If I'm taking the sine of some function, its derivative is the cosine of the function, chained on with the derivative of that function. Cotangent, negative cosecant squared of that function, chained on with the derivative of that function. Okay? This is going to be fun. Who's excited? Just go ahead, raise your hands anytime. Hey, don't look at me like that.
Oh.
Catherine,
Oh,
healthy me. So here we go. Think carefully before you answer. How many functions?
Oh.
1,
Nope.
2,
Nope.
3.
3. Okay. What are they? Hold on, Dexter.
4x to
That's one of them.
sines.
That's one of them.
And then all of it together?
Yeah, well, squared. Yeah.
Yeah.
Good. Okay. So for some of you to visualize it, it might be easier to write this as sine of 4x to the fifth. Whoops. 4x to the fifth, all of that squared, because that's the same thing as sine squared. Catherine, back to you. What function is on the outside? What's the outer layer of the onion?
The square, the exponent.
Beautiful. Okay, so talk me through the derivative here. We're going to start on the outside of the onion and work our way in. F prime of x. How do you take the derivative of a squared function?
Oh, you put 2 out in front,
Mm-hmm.
and then the sine 4x.
No, forget it. Yeah, okay, I'll write that in there. Good. I was going to come back to that, but you're a step ahead of me. Okay, good. What's the exponent up here?
1
Good.
for function.
Yep.
And then.
Well, we know there's a 1 there. We're all part of smart fellows, so we're going to go with that. Okay, so which function is next? The sine of the 4x to the fifth?
Sine.
Good. What's the derivative of sine? I seem to have forgotten.
Cosine.
Okay, cosine of that function. When you're not sure, put it in parentheses. You're almost there. What's the third function?
4x to the fifth.
And the derivative of that is?
20x to the fourth.
Excellent. Well done. That wasn't so bad, was it?
I was able to.
So, let's review. How many functions were there?
3.
Catherine? How many chains?
2.
2 chains? No, you guys don't know 2 chains? Say.
What is that? Function goes to the
Chooses? No. Go research. I do. I'm culture.
I don't know who you either.
What's happening?
So, how can I simplify that? Well, again, this is another example of How far are you willing to go? So one thing I would do is multiply the 2 times the 20 to get 40x to the 4th. But if you wanted to get crazy, I'm sure you remember this from pre-calc. Do you remember that trig identity
Oh no.
with the 2 times?
No.
Okay, then let's skip it.
Oh.
We are done with all of our derivative rules. What you're looking at is a summary of all those derivative rules. However, some of that will not appear to be English to you, because that's not what you know.
Can you do this to us on the test?
Sure.
How is this?
You guys are so negative. Question here in front.
Are we given any of this on the AP test?
Are you going to get any of that on the AP test?
Probably not.
Not a lick of it. About the only thing they give you on the AP test is the volume, or our formulas for 3-dimensional volume figures.
That's helpful.
Yep. As I talked about earlier, some of this stuff is note card worthy. Some of it you've already burned into your brain. I think probably most of you, if not all of you, know that the derivative of sine is cosine.
Yes.
The derivative of cosine is negative sine. Some of you can have no problems at this point taking the power rule, taking the derivative of, let's say, x to the 4th. Some of you are getting better at product rule and quotient rule. All of you are probably confused about chain rule right now, but it'll start to come into play as you practice more and more with it. Okay, questions? All right. That's good for the chain rule. So, what I would like to do is take a 5-minute break, and then when you come back, we will wrap up with the product and quotient rule from yesterday. 2:23. Go.